So yeah, the plan for this talk is to talk about heavy element nucleosynthesis and rare isotope beams. And I was also asked to talk a little bit more about the I process. The rest will be kind of more general, but since there's no other general talk about the I process, I'll focus a little bit more about the I process. So I'll start by a picture that I think most of us have seen before. This is from a paper from Frank and Hendrik from a few years ago that kind of highlights all the different astrophysical processes on the chart of nuclei. So I am an experimental nuclear astrophysicist, and so we like to put everything on the chart of nuclei, as you very well know. And for this particular talk, what I want to highlight is not the black boxes that we typically focus on, but really everything that extends beyond the black boxes, so the stable isotopes. The stable isotopes are still our main observable, and so this is where we focus on when we try to compare our models to observations and so on. But in terms of understanding how a process works, you need to go to the nuclei that participate in this process, and this is where radioactive beams come into play. And hopefully throughout the talk, I'll show you the importance of radioactive beam experiments and what is still needed. So there's a lot of different things going on in terms of radioactive beam experiments, where you need to know a lot of different properties for nuclei, and they are different for each process. And so what I tried to do in this talk is kind of give you an overview. I'm not going deep into any of the processes, but I have little labels in purple color linking to the rest of the talk. So there's definitely overlap with almost every talk that we have during this meeting. So I'll start with the lightest nuclei. So this is nucleosynthesis within classical novae. And I'll say just a few words for each of these processes. Again, you'll learn a lot more as we go through the week. But classical novae are binary systems where you have a white dwarf accreting material from a companion star. And so then you can have a thermonuclear explosion happening. So these are focusing right here at the lighter masses. Even though it's not heavy element nucleosynthesis, I thought I would include it just for completion purposes, because they do need some radioactive beam experiments. And so this is one of the scenarios where almost everything is measured experimentally. Not everything, but almost. So this is one of the most complete pictures we have. However, the missing reactions we have, and they're mainly P-gamma reactions, the missing reactions and some alpha-gamma. The missing reactions we have are very hard to measure. And this is one thing I want to highlight again throughout the talk, is that sometimes it's just hard or impossible, to measure the particular thing we're interested in. And this is where indirect techniques come into play. And so for this particular case, for example, we have beta decay experiments to constrain P-gamma reactions, or it could be transfer reactions instead of measuring the direct P-gamma. And this is again true for many different things. And that was part of working group 4. Again, within working group 4, you will have you will get more information about X-ray bursts. And so X-ray bursts now follow this red line here. That goes along the proton-rich, so the proton drip line, or almost at the proton drip line. So this is definitely where we need radioactive beams radioactive beam facilities, and actually exotic radioactive beams to reach to the most proton-rich isotopes out here. So most of these are not accessible experimentally, at least not for getting direct P-gamma reactions that we need for the RP process. But there are indirect techniques that are either being developed or discussed to try and get there. And of course, with the next generation facilities where we have higher beam intensities, then you can do a lot more. And it's not just P-gamma reactions. You can see here some alpha P's and alpha gamma reactions and so on. So again, you will learn, you'll hear a little bit more about this from Wei-Jia's talk, Wei-Jia Ang's, and of course, working group 4. Moving on to the neutron-rich side, I'll start here with neutron star cross processes. And so this goes not quite to the neutron rib line, but quite far out. And this is this orange lines out here. And as far as there are a lot of different experiments happening, but some of the main experiments happening these days are mass measurements, where you need to understand the masses of these nuclei out here to understand how the different decays will happen in electron captures and so on. And then a lot of work is being done on a relatively new process that was introduced a few years ago, this ERCA cycle, where you have ground state to ground state transitions between different nuclei. And so you have beta decays and electron captures going in a cycle. And at every step, there's a neutrino emitted. And so you start to lose energy in this environment by emitting the emission of neutrinos. So it's very important to understand these ground state to ground state transitions. And again, there's a lot of experiments planned or happening already related to this. The next item I wanted to introduce is supernova explosions, and again a lot of input that goes into supernova explosions and what kind of measurements we need to do. So here I just highlight two parts. One is going on the proton-rich side. This is a NU-P process, which is similar, even though it's a very different environment. It goes in a similar way as the RP process. Again, it's sequential P gamma reactions mainly, but there's the added component where you have these NP reactions that alter a little bit your path, and they overcome some bottlenecks that you have for the RP process. With the NU-P process and these NP reactions, you can overcome that. On the neutron-rich side, there's electron captures that are very important, and these matter a lot in terms of the dynamics of the system, the explosion itself, and the balance at the center of the supernova, pre-supernova and during the supernova. And so for this one, electron captures and beta decays are the two main things that we need. And since electron captures on the neutron-rich side are actually not the easiest thing to measure, this is where again we get indirect techniques. So charge exchange reactions is what is needed to probe this kind of measurements, and you'll see a couple of talks by Evan O'Connor and Remco Zegers discussing exactly these aspects. For some of these, you could get the beta decay rates through total absorption spectroscopy, which is really measuring the beta decay rate itself. However, again, if the thing you're interested in is the electron capture, then you get limited information from measuring the reverse, the beta decay. But again, we can do that and constrain our models and learn something about the theoretical aspect of this description of this process. And then finally, the biggest slide, the slide that has kind of heavy element nucleosynthesis, most of the processes included. And so again, I'm not going to be able to cover much of this, but as you see from my list up here, there's a lot of talks and a lot of speakers covering these topics. But we have the traditional processes would be the S process, neutron capture process, kind of going along the valley of stability. And then you have the R process that goes quite far away from stability, this blue line out here. We will see a lot more variations of these and different environments and so on. And these are the two classic processes to produce the majority of the elements. We also have the P process that is also a classic process, although contributes much less in the abundance distribution of the various elements. And this goes on the proton-rich side, and it's a gamma-induced, it's a photo dissociation process, so it kind of starts at the top going down here. And you can see the list of different aspects, different things that we need for the various processes. We need P gamma, alpha gamma reactions for the P process. There's the majority of the S process and gamma reactions are measured already, but we'll see that there's still some missing, especially on long-lived radioactive nuclei. And then, of course, the R process is a big open question for many of us. So from the observation side, the modeling side, and the experimental side, and the nuclear theory side, because there's just so much unknown and so much information we need to measure so many different nuclear properties that we need, and we just don't have access to the majority of the nuclei just yet. The next generation facilities will give us access to most of them, so that's one of the reasons we're very excited and looking forward to those. And then the last part of this slide I wanted to mention is this I process. For some of you, maybe you haven't heard of the I process before. It is relatively new. And as I mentioned in the beginning, I was asked to introduce the I process in my talk as well. So I stands for intermediate, and it's intermediate between S and R. Intermediate in terms of neutron density. So if you think that the S process is about 10 to the 8 neutrons per square cubic centimeter, and the R process maybe at 10 to the 22. So the I process would be somewhere in between, maybe 10 to the 13, 10 to the 15, that range. It's also intermediate in terms of where it sits on the chart of nuclei. So you see the S process sitting right on the value of stability, and the R process quite far away. And so the I process is somewhere in between, intermediate between again. So let me just show you a little bit. Why do we even need an additional process? We were all happy and doing quite well with just the S and the R process, explaining all the abundances we could see, we could observe in nature. Why do we need another process here? So it started by, of course, by observation. You look at your observables and you're trying to explain the universe by looking at the observables you have. And so for a long time, we just didn't have any observables that could not be explained by the S and the R process or some combination of the two. But it happened maybe, I'll say, I don't know, 20 years ago, starting to have a few stars. And I think the first one was Sakurai's object. So we started with a few stars that had these weird abundances that could not be explained by S or R or a combination of the two processes. And so as an example here, I have the star CS31062-050. It's from two different papers. The first paper here from 2004 shows the abundances, the abundance distribution, the observations for this particular star. And then the different lines show you solar system S process only. So this would be the solid line down here, or R process only. This would be the dashed line, or a combination or a sum of the two. And so what we can see here is that none of these lines really follow what we see in this particular star. And then a few years later, this is Falk Herwig's group from the University of Victoria and the rest of the team. They introduced this I process model where you can see that for the same star, this is still the same star, they could reproduce the whole distribution with their models. So this is just one example. There are now many examples out there. I just wanted to show one example where you really cannot reproduce the abundances with what we had before, and adding the I process now does a good job reproducing. This is still one star. So something I stole from Falk Herwig is this plot. I just like this plot very much. Let me go through this. So this is lanthanum versus europium over barium. Sorry, lanthanum over europium versus barium over lanthanum. So these are just kind of classic heavy elements, and these are many different stars. The different color code is what was identified in this particular library, the JINA base, as, oh, this is an S star, this is an R star, and so on. So what Falk and his team did here was to just have a very simple, naive model where they have the neutron density and they just vary the neutron density and just see where that neutron density, what kind of abundances would that give you. So if they would have the 10 to the 8 neutrons per cubic centimeter like we have for an S process, they would expect to see abundances in this green box. If you would have about 10 to the 20 neutrons per cubic centimeter like you would have for an R process, then you expect abundances to be in this blue box. And so we see some stars sitting here in the S process box and some stars sitting in the R process box. And kind of naively, if I would do a combination of those two, then I would just expect something in between those. But you see there's a bunch of stars sitting over to the side here where it's again one of those things that I can't imagine a scenario where I get this one and this one and I sum them up with any kind of variation and I get an answer that looks like this. So this was another indication that there's something else going on. And so what they did was just change the neutron density starting from 10 to the 8 and just going, this is this dashed line, and starting with 10 to the 8 and slowly going around, increasing the neutron density as you go, and then ending at 10 to the 20. So this is again the scale we have here. And so what you see is that for these intermediate neutron densities, you do hit basically every point on these stars that are sitting here off to the side. And so at least for me being on the outside and just looking at a plot like this, I know this is a simple model, and since then they've done a lot more complex calculations, but I still like to see this plot and to show this plot, because it just shows there's a region where we cannot reproduce in any other way, and all of a sudden you introduce a new process, and this explains it. So of course, you know, going from this to describing, having a realistic description of the problem and of these stars takes a lot of work, and this is where we need to understand this process a little bit better. So again, this is a high-level description of how I understand the I process. So don't shoot. I'm sure you'll get a bit more detail as we go through the week. But if we just say that there's a neutron density we need a neutron density of about 10 to the 13 to 10 to the 15. That's what we need. So something like this was actually introduced about 40 years ago or even more. But since at the time there were no stars that needed to be explained, then it was not investigated a lot more. And recently, now that we have these observations, the motivation to do it, that now there's a lot of work going on with this. So the way it works is that you need a neutron source that will give you that many neutrons. So the neutron source is most probably the carbon-13 alpha N. And to do that, then you would need to be sitting in this helium layer of my simplistic cartoon model of a star. But this is also a reaction that gives neutrons for the S process, not just this one, but this is one of the reactions. And it only gives neutrons that go up to 10 to the 8 or something like that. So you need a way to get more neutrons than what you would get from an S process. And to do that, you need to replenish your reactants. So in this case, if I have a way to produce more carbon-13 here, then I could get more neutrons out. And this is done through this sequence over here. So if I have a carbon-12 P gamma reaction, which would happen here in the hydrogen layer of the star, nitrogen-13 has a half-life of about 10 minutes. So it decays into carbon-13. So this is all great. It produces carbon-13. The problem is that carbon-13 would now be produced in the hydrogen layer, and I need it to be in the helium layer so it can capture alpha particles. And this is where now, you know, in this simplistic model, thank you, Anna. This simplistic model doesn't work very well, because, you know, you don't have enough overlap between the layers to actually to get what we need in terms of the reactions. And this is where, if you have kind of a more realistic model of your star where there's a lot of turbulence and mixing going on, then you can have carbon-13 produced in one layer and somehow travel and go to the other layer, and you can have your neutrons produced. And so for me, kind of trying to explain how we are now into, you know, all this excitement about the I process, we have the motivation for needing a new process, and we have the more realistic astrophysical calculations that show that this is feasible. And so based on those two things, then we're diving deeper into understanding what this can do. So again, I'm an experimentalist, and I want to know what is needed to understand the I process better. So the first step is to see which nuclei participate. And so this colored here next to the black boxes, this is where this is the nuclei that participate in the I process. The good thing here is that almost every nuclear process or property is measured experimentally. The masses are known, the half-lives are known. Maybe there are some isomers that are not well known, but almost everything is known for these nuclei. The one thing that is missing is neutron capture reactions. And this, again, it's very hard to measure neutron capture reactions. We need indirect techniques, and this is part of my research, but I'm not going to go into detail here. But in terms of the motivation and what we need in terms of radioactive beam experiments, we need neutron capture reactions. And we do have access to some of these with current facilities. And of course, with the next generation facilities, we will have access to all of them. So there is, let's say, hope or a solid plan to measure experimentally or constrain experimentally most of these nuclei and have the I process on a solid footing very soon. Okay, so putting everything together, I got the note for 5 minutes. Now I'm probably down to 3 minutes. So I wanted to just have a slide that shows everything. I showed you the various processes and what is it that we need for each of them, and we need a lot. You need half-life, better decay properties, half-life and better delayed neutron emission. You need neutron captures, masses. So you'll see a lot of talks throughout the week that focus on each of them. So Remco Zegers will tell you about charge exchange, and Jason Clark will tell you about nuclear masses and so on. So there is a lot going on in the field, and I'm not going to try and even cover everything. I just wanted to have everything on a slide that shows you everything that we need to measure, and we are working hard on that. And of course, moving to the future, we will have access to a lot more nuclei, which is probably the most important thing right now. So I'll say most of the techniques we need to measure these are established. We are coming up with new ideas and new techniques every day, but we do have ways to measure most of these properties. It's just that for a lot of them, we don't have access to the beams we need, and this is where we need the facilities. And also a lot of these, I have the labels here, most of these experiments are not all done at the same facility or with the same type of beams, you know, in terms of energies and so on. So we need a variety. We need diversity in our facilities, in our equipment. So we all need to work together to contribute to this problem. So again, there are a lot of existing nuclear radioactive beam facilities around the world. So you'll hear probably a little bit about TRIUMPH and RIKEN from Iris Dillman later today. René Rayford, I assume he will talk about GSI a little bit and maybe FAIR for the future. So I decided for this talk to just give you a couple of examples from the US, which are Atlas, and of course NSCL was just completed, but FRIB is the next generation lab. So Atlas here is a current facility, and so I'll just highlight a couple of things that they're coming up with new upgrades. One is the new Caribou that gives you access to nuclei out here. They have Razor to get radioactive beams down at the lowest masses, and very exciting, they are planning the A equals 126 factory to give access to nuclei out here that we don't have access to right now. And then, of course, I can't have a talk like this without FRIB. Yes, and I see you. Let me just finish this for 30 seconds. And so the FRIB is the next generation radioactive beam facility in the US. I'm sure you've all heard about FRIB before, but the exciting thing is that it will give us access to all of these radioactive beams far from stability and going almost to the neutron rip line for most of them. The first call for proposals was announced, so if you're interested to run experiments, you can contact anyone at FRIB or anyone in the community, really. And so I will just finish here, and thank you for your attention.